Welcome to this explainer. I'm thrilled you're here because today we're decoding something that's practically invisible yet absolutely crucial to our modern lives. We're looking at the hidden mathematical mechanics keeping our electrical grid alive. When you flip a switch, you just expect the lights to come on. But the delicate, behind-the-scenes physics making that happen is nothing short of an engineering marvel.
Okay, let's dive into this. We constantly hear about power lines, generators, and transformers, but what is actually straining our power infrastructure? Why do these massive, robust systems experience invisible strain and incredibly costly inefficiencies, even when they seem to be running perfectly fine? Well, the answer lies in the very nature of alternating current, and a hidden phantom force that engineers have to constantly battle. To make sense of this, we'll follow a super simple roadmap. 1. The three types of power. 2. The power factor problem. 3. The power of compensation. And finally, 4. The actual tools of the trade. So, Section 1. The three types of power. The electricity flowing into our world isn't just one single, simple force. The first type is active power, which engineers represent with the letter P. You can think of this as the literal worker of the grid. Measured in watts or kilowatts, this is the power that does the actual useful work. When your space heater generates heat or a massive factory motor spins to run a conveyor belt, that tangible result you can actually see and feel, that's active power in action. But here's where it gets kind of weird. Enter reactive power, or Q. Think of this as the grid's phantom power. You can't use it to light a bulb, and you definitely can't use it to toast your bread. Instead, it just endlessly oscillates back and forth. It acts as a necessary sustaining force to keep magnetic fields alive and massive transformers and motors. Without this invisible ghost, those machines literally just wouldn't spin. Which brings us to the third type, apparent power, or S. Because the grid feels the combined weight of both active and reactive power, we have to look at their vector sum. So S equals the square root of P squared plus Q squared. Basically, this is the true heavy burden the electrical grid actually has to carry. And this brilliantly illustrates how it all ties together. You've got P doing the real work, Q sustaining the necessary magnetic fields, and S representing the ultimate toll on the grid. Managing all three of these is absolutely the secret to a healthy electrical system. Moving right along to Section 2, the power factor problem. What exactly happens when our industrial world skews this delicate balance? It all comes down to a really simple ratio. Power factor is just active power divided by apparent power. In a perfect world, that ratio is a clean one. But when a massive factory flips on its heavy induction motors, it absolutely chugs reactive power. Apparent power balloons, and your power factor plummets. Suddenly, you're demanding way more capacity from the grid just to get the exact same amount of actual work done. And this creates a pretty terrible domino effect. Step 1, a factory demands high reactive power. Step 2, because the power factor drops, the utility company is forced to supply more total current through the lines just to deliver the required working power. Step 3, pushing all that extra current through the wires creates intense electrical friction, known as I²R heat losses. The grid is literally cooking itself, wasting energy as heat. And finally, Step 4, all that extra current dragging through the lines causes severe voltage drops, destabilizing the network and eating up overall grid capacity. That brings us to Section 3. The power of compensation. Let's meet the engineering hero that saves our melting grids. So, the crucial point here is distance. In an uncompensated grid, that useless reactive power has to travel all the way from a distant power plant to a factory motor, clogging up the whole system. But by installing devices locally, right next to the load, we can supply or absorb that reactive power on the spot. We keep it completely off the main highways of our distribution network. The benefits of doing this are, frankly, massive. First, voltage regulation. It stabilizes the lines. Second, reduced line losses, meaning way less energy wasted as heat. And third, the holy grail, increased system capacity. By clearing that useless traffic off the lines, we can push more actual working power through the exact same infrastructure. It's essentially an invisible multi-million-dollar upgrade to the grid. Which leads us to our final section, 4, tools of the trade. Let's open up the engineering playbook to see the physical hardware used to pull this off. The first and really most common industrial method is the use of shunt capacitors. These are fixed, passive components. Because inductive loads, like motors, consume reactive power and create what's called a lagging current, engineers place capacitor banks in parallel with the load. Capacitors do the exact opposite.
they generate leading reactive power. They basically act as local storage banks that perfectly cancel out that inductive demand right at the source.
But sometimes the grid has the exact opposite problem. On very long, lightly loaded high-voltage transmission lines, the natural capacitance of the lines themselves can actually generate too much reactive power. This causes the Ferranti effect, leading to dangerously high voltages at the receiving end. To stop the lines from essentially overcharging themselves, engineers deploy shunt reactors. These are giant inductors used to absorb that excess power before it causes a catastrophic spike.
Another seriously brilliant passive tool is the series capacitor. Placed directly on the high-voltage lines, they reduce the line's natural resistance to current changes. Mathematically, it effectively shortens the electrical length of the transmission line. It's almost like widening a bottleneck on a highway, which greatly increases the active power that can rush across it.
Now, let's see how this builds into something even more advanced. Those previous tools, they were static. They just sit there and do their one job. But the modern grid has constantly shifting demands. For that, we need dynamic compensation. We're talking advanced hardware capable of dynamic sub-cycle responses that react to grid instability in literally fractions of a second.
And the most fascinating heavy-duty tool in this dynamic arsenal is the synchronous condenser. There's an incredible quote from our source material that says, "A synchronous condenser is essentially a synchronous motor running without a mechanical load." Just think about that for a second. Engineers take a massive, heavy industrial motor, attach it to absolutely nothing, and just let it spin freely. No way, right? So why run a massive motor attached to nothing? Well, by adjusting the DC magnetic field of its spinning rotor, this machine can smoothly generate or absorb reactive power on the fly to perfectly balance the grid. Plus, because these are gigantic pieces of rotating metal, they add immense physical mass and mechanical inertia to the entire electrical system. They act like massive physical shock absorbers, naturally stabilizing the grid's frequency against sudden load changes or system faults. It's truly incredible to think that every single time you turn on a light bulb, an elaborate dance of active, reactive, and apparent power is happening in the background, carefully managed by massive free-spinning motors and local capacitor banks. It really leaves you wondering, if these invisible mathematical forces and hidden engineering tricks govern our entire power grid, what other invisible mechanics are secretly sustaining the rest of our modern world? Keep questioning, keep learning, and thank you so much for exploring the hidden grid with me on this explainer today.